Hello everyone, my name is Kushal Singh and today we're going to talk about AI clone using deep reinforcement learning. So yep, let's get into it. Yep, here it is. So now what we are going to do in this project is we are going to develop an AI clone of Super Mario Bros. Using deep reinforcement learning. Now what is deep reinforcement learning? Reinforcement learning is nothing but a part of deep learning. Reinforcement learning is, if I have to explain you in simpler words, there is an agent. In our case, it is Mario. It takes some steps, it takes some actions, and based on those actions, we give it a reward. If it takes a good step, we give it a better reward. If it takes a wrong step, then we can deduct the points from it. And based on those rewards and actions and iterations, it can keep learning things and it can keep improving. So now that you have understood what deep reinforcement learning is, let's see what's the need of this. Like, why are we actually doing it? So, here is our problem statement. So, what is the thing that annoys the offline gamers most? It is completing a level, completing a game, and then you don't have anything else to do. You're getting bored after playing it so many times. What else can you do? So, uh, yeah, that's where our reinforcement learning comes in. What is the solution for this? Solution is we are going to develop a model which can play a game by itself. It can adapt, it can learn your moves, it can learn your play style, and it can cross the game easily. So you can just train your model, you can compete with it, and there are already so many gamers and basically gaming agencies which are using deep reinforcement learning. Even in tech and youth, there is a clone fighting system where you can fight with yourself. So this is the solution we are providing, and yep. Let's see how we're going to do it. First of all, our main task was how to set up Python and connect it with Super Mario Bros. Like how we're going to play Super Mario Bros. By using Python. For that, we have used the gym library, the OpenAI gym library. It helps you to set up the multiple game environments inside Python. And then what we have done is we have simplified the movements because there are varieties, different combination sets in Super Mario that you can use, and it will be so hectic for our model to learn those steps and trying those things. So that's why we have just used the different, only I think five or six. Yes, we have used only six different movements, basically to jump, to right, and duck and shoot the power ups if you have any. So this is nothing but basically simplifying all the movements. And this comes the main part, basically pre-processing the game. So how do we make sure that whatever our model is learning is actually reliable or efficient? I mean, we cannot give the bad data because good data means good training, means good model. So how do we actually convert bad data into good data? So we are using the real-time game images here. There is no pre-trained data set, or there is no images data set here. We are using the actual real-time images, and it is learning by iterating itself over and over and over. So what we have done is, first we have taken a game scenario. For example, if we start the game, there is Mario and it starts, taking random steps. And after that, we turn it into the grayscale from that, colored image or that colored video from whichever our model is, learning things. We have turned it into grayscale. What it does, it reduces the channels by two measures, from RGB to the grayscale. So it removes the unnecessary noise and unnecessary data which might our model learn. So, yep, this was the first major thing that we done. It reduced around 70% data that your model has to learn because it was unnecessary. So, and the second thing was using the frame stacking technique. Basically, it takes three or four frames like before any instance, and it also learns from it. And then comes the main part, importing our model. We have tried it two different models, the PPO model and DDQN algorithm. So I will share the results later in the video. So basically what we did is we imported the two models, we ran them for different steps. Yeah, that I'll tell you later when I will show you the results that how many steps it took to clear the level. And yes, we trained it and then we tried it out. So let's don't waste any time and get straight into the results. Like, okay, yeah, slide, and let me show you a real demo of the code. So here it is. Just let me run this code. It will take some minutes. So yes, here it is. It has started running. So now what you are seeing here is the DDQN algorithm, which was, better than PPO. So this is the most efficient model that we tried, and this is the results that you're seeing. Basically, yes, our Mario is doing great. It can get stuck, but as you see, it has cleared the level. Oh, I mean, really, in the first try. This was only fourth iteration, and it almost crossed the level. So DDQ and all algorithm gave us the results, which were more accurate and more advanced than the PPO algorithm. As you can see, our Mario is stuck right now, but after some time, after some iterations, it can learn and it will cross this pipe. So yep, this is it. And our PPO algorithm was also working, but it was not as good as this model. It was getting stuck. Now, on coming on to the results, our DDQ algorithm took only 40,000 steps to clear a level, around 40,000 iterations, and it cleared this first level. Whereas our PPO algorithm took around 4 million steps. Yes, 4 million steps just to clear one level. And you can see the difference, obviously. So yeah, we can try different algorithms. You can use different methodologies, different reward systems, and you can try it by yourself. So that's all from my side. I will just close it. I think this was the demo. As you can see, only 5 iterations, and in the fourth iteration, we got around 635 reward. And yes, this was the iteration I was talking about where our Mario got so far in the game. So the reward it got was 1331, which is a good reward by ourselves. So, yeah, I think